good morning, or good afternoon, or good evening. So my name is Chris de Meester from XenomatiX, responsible for sales and business developments, and I will be presenting today together with Tim Massard from the Belgian Road Research Center. First of all, I'd like to thank the IRF to give us, as a new member, the opportunity to reach out to you all. I also want to thank the BRRC for the successful collaboration that we have. And of course, most of all, I want to thank you all for showing up and for showing your interest in this exciting new technology roadmap we are presenting today. Road scanning, innovation, now and the future. On the agenda for today, we start with a short company presentation, so you know who we are. Then Tim will present a summary of the road quality measures and means that you probably all know, and he will make the link to the vision towards the future, the near future, I would say. After that, I will present the new road scanning LiDAR. I'll talk about the products. We'll set it up on a vehicle, and then all together we get in the car and we go for rides. After the demonstration, I will shortly discuss a few other cases that might interest you. And we will end with the summary, how we can help you save time and resources, because that is the final purpose. Okay, company introduction. Start with XenomatiX. XenomatiX is a company focusing on the development and the commercialization of LiDAR sensors. And LiDAR, for those who do not know, LiDAR stands for light detection and ranging. So measuring the geometry of the environment by sending out invisible light and capturing the reflected photons, the reflected light. XenomatiX is founded in 2013, so kind of a startup scale-up, based on the invention of a professor from the University of Antwerp. He had a great idea on how to solve the requests from the automotive market. Let me explain. When we look on this time scale, everybody remembers the outcome of the Google car with the spinning LiDAR as a mushroom on the roof. That mushroom, as I call it, contained cameras and LiDARs to measure the full environment around the Google car. And everybody was excited, not in the least the automotive industry. Then it got their attention. LiDAR technology was known, but the usage of LiDAR technology gave a perspective to them to realize safe and reliable autonomous driving. But to make this happen, the car industry asked to make that mushroom, that big thing on the roof, more robust and reliable. And they asked for what they call so-called solid state solution, meaning no moving parts, robust for the car. And over time, as you see here, many companies have worked on LiDAR, modifying the spinning LiDAR by miniaturizing the scanning mechanism. Until yesterday, the LiDARs were still scanning and still using microscopic small mechanical moving components, so not robust enough. We as XenomatiX, from the beginning, we work solely on true solid-state LiDAR. Our headquarters is located in Belgium. We have offices in Germany, in the US, in Detroit, and in China. And we have also distributors. In the US, they're located in California, in Japan, and in South Korea. Tim, can I ask you to shortly present the Belgian Road Research Center?
Thank you, Chris, for the introduction. Yes, of course. My name is Tim Massard. I'm a researcher in the Belgium Road Research Center. We are an impartial research center since 1952. We have different divisions, going from geotechnics to pavements and to road management. I am working in the division Road and Asset Management. Our key activities are research and development, technical assistances, and knowledge sharing, and this for all stakeholders in the road sector. Let me now summarize the measures and means for road scanning that we all know, and then pass the bridge to our vision for road scanning in the future. we can observe different road network owners. One of them are national road authorities, also known as NRAs. These entities have a quite big road network to manage. Therefore, they are using different technologies to measure fast several technical parameters like longitudinal evenness. For this parameter, different indicators are used. IRI is the best known, and software like Proval is broadly used. Other parameters are transversal evenness, crack detection, skid resistance, etc. Here are some different technologies. At the left, we can see the APL or Longitudinal Profile Analyzer. This is an inertial profiler. The trailers are towed by a van to measure the longitudinal profile of a road. We do this in both wheel tracks. The drawback of this system is that you have to keep a constant speed at all times and you only obtain the longitudinal profile. An alternative for APL is a laser profilometer or laser profiler. We measure also a longitudinal profile, in this case mounted in a small trailer towed by a scooter to measure bicycle paths. Here we have no speed constraints, but we only get the longitudinal profile as a result. On top in the middle, we see a LiDAR scanner. This device is able to measure the transverse profile as well as a reconstruction of a road in 3D. And on the right, we have two different multifunctional vehicles equipped with multiple LiDARs, cameras, lasers, etc., and is able to measure different technical parameters in one run at different speeds. Drawback here is the cost varying between $1 and $1.5 million and therefore out of reach for regional network owners. With regional network owners, we think of cities or municipalities with less budget. For these networks, we see different approaches, mostly based on visual inspections, relying on a well-defined methodology. Drawback with these methods is that they are labor intensive and they need well-trained inspectors to obtain the required objectivity and repeatability. In other words, cheaper on equipment, but more expensive on labor. All these technologies and methodologies are well established. But how can we do this in the future in a more efficient, reliable, and more affordable way? This is what we, XenomatiX and BRRC, are looking for. Innovative approaches for affordable solutions for performant and cost-effective road management, taking advantage of upcoming technologies. So here comes the link between XenomatiX, more known as a high-tech automotive LiDAR company, and BRRC, focusing on road management innovations. Autonomous driving is coming closer every day, and in the near future, all cars will be equipped with many sensors like cameras, LiDARs, etc., to allow for increasing levels of autonomous driving. Today, the technology is going from research at the left to series implementation, and this both for passenger cars as utility vehicles. The eyes of the next generation vehicles will allow to drive, but also will allow to measure and evaluate the pavements and other assets in public space. This is how we see the timeline on pavement assessment in the future. Today, what soon will become yesterday, we had dedicated vehicles like multifunctional equipments and visual inspections. This is what the whole world is doing today. Tomorrow, but already today, with this new road LiDAR, we are able to use more affordable technologies on an everyday vehicle to collect data. In the near future, and with this flexible and affordable measuring system, data can be collected, for example, by utility services like garbage collectors or mail delivery vans. And later, with higher level of autonomous driving breaking through, this technology will be implemented in our future cars and data will be collected by all road users with so-called crowdsourcing or big data. And on top, you can see the drastically decreasing cost per mile or kilometer measured. And that's something for all road management stakeholders to look out for, isn't it? So this presentation today focuses on step 2, already new and innovative, but is based on the same technology that will be implemented in autonomous cars coming up in step 3 and 4 in the next decade.
Thank you, Tim. Thank you. So let's zoom in on this new road lidar. This road lidar is a flexible standalone sensor that you can mount on any vehicle. Mostly it's mounted on the roof, and the sensor sends out thousands of laser beams directly to the road and capture the reflected light. And then with an algorithm of triangulation, the full geometry of the road is calculated. Triangulation you can compare with the GPS and the satellites. As you can see, the beams are grouped in bands, and each band consists of hundreds of laser beams. The sensor itself, it's not scanning, but the movement of the car. With the movement of the car, the beams all move around and move over the road, fill up the gaps, and get a full scanning of the road. That's why we call this kind of lidar an area scanner, because it measures a whole area in one spot. All those bands together, they combine to thousands of laser beams, and the same spot on the road will be scanned by many different beams. And this results in a high resolution and a high accuracy. In the software, it will look like this. And this is what we will recognize during the demonstration. These are the bands, each band hundreds of laser beams, and the gaps in between that will be filled by the movement of the car. So this means that the whole road is digitized over more than one lane wide, and any cross section in the longitudinal or transversal direction can be taken. This can be done while driving, so online, or you can do it also afterwards in post-processing. Here on the right, you see a longitudinal cross section while driving. It should be a movie. Let me go back and forward. Yeah, so the movie is not so clear. Apologize for that. The bandwidth. So here you see in this measurement that really the road was moving up and down while traveling over the roads. And so it had a kind of undulation, which is not good for safety on highways. Besides the geometry and the cross sections that we get, this lidar also measures the intensity. And intensity is how much photons does the road reflect. And as you know, painted road markings reflect more light than unpainted, or more bright stones will reflect more than less bright stones. So it means that road markings, I'm thinking of lines, I'm thinking of a bus stop or a stop sign, will be detected by this lidar as well. So if you combine the 3D geometry with the intensity information, and I give it 1 dimension, we are already at 4 dimensions. Later we'll add a camera image, adding 2 more dimensions to obtain 6 dimensions in total. Advantage of this technology is that there's no speed limitation as required for some of the equipment that Tim was presenting before. Here you can drive at any speeds and at varying speeds. There's no limitation here. And with the active illumination technology, which lidar is, measuring at night, outside rush hours, I would say, that's no issue either. And when it rains, and that's pretty important one, I think, this lidar will measure through the water and still be capable of measuring rutting, for instance, which is most dangerous when it is raining. You can also measure it while it is raining. And that is actually a consequence of the choice of the laser wavelength that we use in this lidar, the infrared lights. Here are the specifications of the lidar. I'm not going to go in detail. If you have questions, we can come back to it. It gives a resolution and accuracy. And for those who are interested, of course, we are very happy to share a specification sheet with you. Okay, let's get some action. Let's mount a road lidar on a car and go for a ride. So to mount it on a car, here you have the LiDAR itself. There you have the controller unit that you put on the passenger seat or in the trunk, and the cable connecting it, and that's actually it. That are just some switches, so nothing special. Additionally, because you do want to have the speed information, and that you can get from the cam of the car with a cam connector, or you can also have it from a GNSS. The GNSS information is always interesting to have, even if it's not needed for the speed of the car, to connect with the rest of the data. And to increase, as I said, from the 4 dimensions to the 6 dimensions, we add a camera. You can also combine a camera with a GNSS in a so-called image box, and then you have both. That is what we have been doing recently. So this is the equipment, as simple as it is, and you can mount it on any kind of vehicle, on your and my vehicle, on a garbage truck or whatever. So required to set it up is one person, any person, I would say, a standard car, a roof rack, and then 30 minutes of your time. 30 minutes of your time is after training by our engineers. And what is the result? This is the result. This is on our Volvo, where you have the LiDAR on top, looking backward in this position with the camera and GNSS. All the 6 dimensions plus the GNSS annotation. So as you see, this is the same system as before, but oriented backwards, and that we call the rear view system. So same thing, but now the car is driving the other way. The same beams are sent out to the road and measuring the road. We see the same bands, and each band with hundreds of lasers, altogether thousands of lasers. I repeat myself. And once the car is moving, all those gaps fill up, and we construct during the whole ride a full, complete digital road. Okay, we're almost ready to start. So we go for the demonstration. Let me see here that I get it right. First, where do we go? For this demo, we chose to drive around in Brussels because that's nearby where BRRC and we are located. And it's also because we use that measurements for research we do together with Belgian Road Research Center. So here, okay, software ready to go. You remember the bands of lasers. We stand still. Let me explain one more time while we stand still. On the left side, you see the laser bundles. As long as we stand still, it's always the same part of the road that is measured. It's only when we move that we construct the full road and that we fill the gaps. Important to understand is the color code that you see here. Green means that it's the height value of a flat surface underneath the car. Blue means that it's below that flat surface, so there's a pothole or something, or a gap. And yellow and red means that it's above, so a bump or a speed breaker or something, with a different scale that we can change. This is the 3D data, and on the right you see the camera. One more thing, in the software we can present the digital data in 2 directions. Here we will start with showing it while the car is driving backwards, I would say. So with the camera image processing this way, also the LiDAR or the geometrical data will process in the same direction. During the demo, I will make some sections, so cross sections, and then that is always referred to the position of the driver. And so I will turn this image around, but you will see, no worries. Okay, everybody ready? Let's buckle up and let's go. So you have the bands, we have the camera image and aligned, and we start driving. You see the different bands are moving with the car. So we're constructing, the gaps are filled, and we're constructing the full digital roads. You see the different color codes already. You see the scale on top. You see there we go from asphalt to cobblestone, and already on the left side we have some elevation, kind of speed bump. And on the right side we have some subsidence. So there we have the blue color. So clearly there is some damage or some modification on the road. Besides the geometry, we show the intensity here, and here the stones are reflecting more than the cobblestone or asphalt. Just after the speed bump, there's again a subsidence. We see detail, we see the blocks from the parking cars that separates the parking cars from the roads. We see blue, yellow, red, depending on the scale we use, but you see even the detail of the cobblestone itself. You see the shape or the dimension of the cobblestone. That kind of detail we go with the LiDAR. On the side, you see the blue. Here, that's an interesting point. We have some manholes, and you see they don't fit completely with the road. The cobblestones around are a little higher on that side than this. So let's take a cross section. Cross section, left side on the car, left side it's flat. On the right side on the car, there's substance indeed. That's on the right side of the car, now in the position as we show it during the demo. So every color is only visualization. There's another substance. The color code is visualization. Behind our numerical values that can be treated. We almost missed a gap here. We have a default on the joints on the two asphalt layers. Let me zoom in with the scale and take a cross section. And here indeed on the left side again, let me rotate, left back side of the car, there is some damage in the asphalt, in the road. And with the blue color because it's a hole. I'll keep this scale. So on the side you see the blue. Here again we see some damage on the joint of the asphalt. We see it in color. Again, the computer will see that in numerical values. While we drive around, sometimes you see the wet road, and when it's blue, then there is some geometrical differences. Here we have some serious damage, I would say, or bad repair, where we have the asphalt not well repaired. Let's take a measure to have numerical values. And indeed, on the left side of the driver's side, left side behind, we have subsidence of the asphalt, and not just a bit. We can also show it intensity. Algorithms will use both intensity and geometrical data to detect what kind of damage it can be, and then calculate the depth of the pothole or the damage. If you watch clearly on the left side of the car, right side on your screen, you see the joint of the asphalt sometimes becoming blue. That meaning that there is indeed a hole, or there is some depth in between the two combinations of the asphalt layers. Now before finishing, let's see if we see some minor. Here we see some minor degradation of the roads starting up. So you're showing the intensity, you're not always sure, is it wet or is it a geometrical default already? Here clearly we see it is a default. Okay. Okay, I think that's good for our rides. Let me summarize the rides. I first want to emphasize that it's a demonstration but it's a real measurement. So with the actual software and real analysis that you can do online or in post-processing. I summarize what we've seen. We drove through Brussels, for those who know Brussels, on asphalt and on the famous Belgian cobblestone pavements, of course. We passed pedestrian crossings that were in the same time also speed breakers, looking at varying road levels and different damages. Remember the damage here that we almost missed. We can measure that damage. We see it in color code. The computer looks at it in cross sections or all the geometry of that damage and can then come up with an index or a quality evaluation. We had a look at those manholes that were not fully in line and some subsidence of the manholes itself compared to the roads. We had extra subsidence here, kind of detail. We take cross sections on the fly or in post-processing. If this is again the same part of the roads where we go over the speed bump here that you see on the red color codes. Here we have two longitudinal sections, a yellow one and a blue one. The yellow one here and the blue one both go over the speed breaker. Fine, the speed breaker height is 120 millimeter high. We see there's a little issue though when we end at the end of the speed breaker and go back from cobblestone to asphalt. It's not a really nice joint. For bicyclists it might be hard. And there's some elevation. If you look at the transversal cross section that you can take, we take three: red, yellow and green. The red one is, as you see here, across a manhole. The manhole is a flat area at a certain level. Just before the speed breaker, we take another section. Here we see already in the blue color that it's deeper here than it is here. So indeed, there is some inclination, some road curvature. It's not rutting, but the algorithm can detect its inclination. And at the level of the speed breaker, we have the green transversal cross section, which is at a higher level, as you see, and more in a convex shape, as we expected. I remember the intensity information, that's the fourth dimension. We can detect any kind of road markings or zebra crossing with more reflective stones used. This is a summary of the presentation of the demonstration from the right that we all got together. Okay, let's go over a few other use cases making use of this new 6-dimensional LiDAR. 6-dimensional, I repeat, 3D in geometry, 1 dimension, I call it intensity, and then the 2D dimensions from the camera. Here we have an example of a car manufacturer, Ford. Ford is interested in the IRI on public roads and on their own proving grounds. They want to match what is the roughness on public roads and what is the roughness on the proving grounds to know where they have to drive to tune their damping, their suspension. So proving grounds, it's very important for them. Proving grounds, the road profiles need to stay constant and therefore they need maintenance, because they want to do measurements today and compare the results of their suspension or whatever with the measurements they did a year ago. And the only thing that can change is the suspension, not the road. They want that to be constant. So completely different application probably than most of the audience today. I go for another challenging one. Another case is from a very innovative road construction company. And here you see the movie that is working. You see there is indeed some undulation on that highway. This road construction company actually wants to use it before, after, and even during roadworks to see what is the quality of the road that they have to, or that they have repaired, or that they are repairing. And the focus for them lies on the undulation, the evenness, the qualification of that, and the quantification. We even think of that this kind of measurements will allow to apply for roadworks where the road owner does not know yet whether it's a good quality of the road or not. So the road construction could go to the authorities and say, I think it's time to give this road an upgrade because it's getting dangerous. I don't know if the road authorities would like it so much, but it's a very innovative company. Another thing, if we talk about roads, it's in a broad sense. So road means also airport runways or harbor quays or even off-road tracks. So many and always the same information that you get in very much detail to be analyzed. There are two more use cases. Tim, you know a little more about those use cases. Can you maybe comment on those?
Sure, Chris. This is a use case where we have compared the raw data from the XenomatiX and APL to evaluate the longitudinal profile. So here you see the first step where we have synchronized both profiles. This profile is coming from one wheel track on a newly paved road in Belgium. So from the XenomatiX data, we used only one line, so only one profile, of the full data set, and for the APL, we only have this one line in the wheel track. Instead of using Profile software to calculate the IRI, we have used the Belgian technical parameter to evaluate the evenness. With this test, we could conclude that the measured road data from the XenomatiX coincide with that from other certified equipment, and that the XenomatiX achieves the level of a Class 1 profiler. In this test, this slide shows that we got somewhat further in the analyze comparison. On the upper part of the slide, you see 3 graphs. These are the evenness parameters we use in Belgium, called the evenness coefficient. At the left, we see the evenness coefficient 2.5, where we look at wavelengths of 2.5 meter. In the middle, we see the evenness coefficient 10 with wavelengths of 10 meter, and on the right, the evenness coefficient 40 with wavelengths of 40 meter. These parameters are calculated on the raw profile with the same algorithm, and as we can see in the correlation graphs, we are very satisfied with the results. Knowing, of course, from the previous slide that the digital raw data matched, this was, of course, not a surprise. But as conclusion for this case study, so the APL, we only have 2 longitudinal profiles and we need a fixed speed. With the XenomatiX, we have a longitudinal profile every centimeter in lateral direction, and we have no speed constraints.
Thank you, Tim. Thank you. So what you here see is the correlation that Tim was referring to, correlation between the APL as a certified profiler and the XenomatiX measurements. Thank you, Tim. So now the question and the vision, what we want to present today, what to do with all this digital data. We want to go from data to information. With just mathematical calculation, we can obtain, I would say, the traditional measures like IRI or the longitudinal transversal evenness index, rutting index, and so on. But even if applying artificial intelligence, we can come up with road markings indices or crack indices, which already exist, but we want to do that automatically based on the numerical values gotten from this LiDAR. So this is really the future where we're going to. To summarize the products as such, the characteristics of this new road LiDAR. When comparison, it's proven to match a Class 1 profiler. It does generate abundance of data with 6 dimensions in total, including the GPS annotation. So there's a lot of information there that you can use. It's flexible to mount on any vehicle, and it's affordable compared to some of the other equipments. It can be used for any road, in different weather, and at variable speeds. And with the performance artificial intelligence, we can go to geometrical and intensity data and information in indices. And not to forget, this kind of LiDAR will be integrated in the car you and I will be driving in the future. So in the future, no special vehicle, no extra equipment, no extra resources will be required to collect that data for pavement management system. Question will be, of course, who owns that data? We can discuss on that later. So to bring the Q&A to life, we're almost at the end of the presentation. Let me suggest how we can help you save time and resources starting today or tomorrow. What is XenomatiX offering? We are offering services, equipment and software, and tailored solutions. When we talk about services, this can be generic road data that we have off the shelf available. Of course, you might be interested in a specific road for which we can do customized road measurement campaigns. And for both, we can go to analysis and also customized analysis where you prefer it. Equipment, we described the LiDAR, and that's equipment, hardware and software included to do that analysis. And for tailored solutions, it's customized road scanning solutions. So we discussed with companies to integrate the LiDAR in other equipment even, or to do some special indices that we have not done yet. And with the full support of BRRC, we are also able to offer, it's more there that take the lead, the research on EMS, on asset management systems. To focus on the first data set, because that is available off the shelf, let me give you a quick glance of what you will find on our website after the webinar. So what we have, if you want to have a flavor and you want some data to do some testing or simulation or analysis with your tools, different road types, cobblestone, of course, we're in Belgium, gentle and rough, and I guarantee you we have both in Belgium, concrete roads, gravel roads, dirt roads, off-roads, tunnel. These are the sets that we have pre-recorded and that is available for sale in different formats. So either you're only interested in the 3D geometry and you want it in CSV format. Maybe you want to do 2D image as well. Most people prefer it in a CRG format. That's for simulation and simulation, the mostly used. Yes or no with the camera image as part of it. You might be interested in the intensity or reflectivity data alone, in the grayscale format, as you know. Again, with or without the camera image. You might be interested only in wheel tracks, so some post-processing already done or cross-section taken, I would say. Again, available in CSV format, or you want the whole thing and the whole package. These are the standards, what's standard packages, data sets that we pre-recorded and that anybody can ask for. Okay, we are at the end of the presentation. I hope, Brendan, that we are within the time limits that you gave us. Here you find the coordinates with our marketing specialists. Brendan will also share after the seminar link to the video and with extra contact persons for the different locations where we are located, US or Europe. Those from China, we can also provide that. But here are the contacts. If you want to know more and have a more private conversation, please feel free to contact us and we get in touch with you very soon. Thank you.
Thank you, Chris. Thank you, Tim. Thank you for that. You were extremely punctual and I think concise in your overview. You've provided us with a compelling set of insights into the applications offered by advanced road scanning technology. Thank you in particular for the drive through my neighborhood. There were streets that I think it's fair to say were in a worse state than the ones you showed. But by and large, I think it was a pretty good overview of let's say, the urban landscape that we have to offer here in Brussels. As Chris highlighted, I understand that there is a recorded version of the demonstration that we've just seen that is available on the XenomatiX website, and we will be providing a link to that video as part of the proceedings of this event. So we're now, of course, entering the Q&A segment of the webinar, and whilst you continue preparing your questions, and we've already received quite a few, just a reminder that this webinar is hosted by the International Road Federation's Committee on Road Asset Management. If you'd like to receive more information about the work of the committee, the benefits of IRF membership, or upcoming asset management committees, such as our online training program, which opens June 1st, please contact me by email after this webinar. So, Tim and Chris, let's get you started with a couple of questions. As with anything that is kind of a, new, there are lots of questions that have come in on, how the system works, and I'll get to those in just a minute. But I wanted to start you off on a more fundamental question, which I thought was very interesting and which really relates to how road agencies work. So let me read it. Given that most road management decisions require time and budget, except for pothole repairs and the like, how do you see real-time road monitoring being used in systematic road management? And can you discuss, how you envision the use of high-frequency data collection to benefit road management?
That's a very good question. Let me scroll back on one of the slides of Tim, where we see how we vision the future. The road LiDAR, as we said, can be mounted on any car. And we see in the future that a lot of data can be collected without specific vehicles, without specific resources. And that can be in the next stages, we think, by utility services like garbage truck. The garbage truck gets the road LiDAR. It does part of the community. Then the next week, the LiDAR is mounted on another garbage truck that is measuring the other part of the community, and so on and so on. And after a month or two, the whole community is digitized. And if you can do that so regularly, then you can really see what is the degradation. And that is what we think in the further evolution of data collection and big data, and that's going to happen anyhow. All those hurdles will be taken. That data will be collected, will be sent from the garbage truck to the clouds and then be gathered. There can be analysis on the garbage truck, or it can be offline. That's how we see that it's going to help the pavement managed system. And then all that data should be managed by that system.
Yeah, thank you very much for that response. And I guess the audience member in question was also kind of highlighting a bit of a discrepancy between, on the one hand, the fact that road agencies are now going to receive a kind of a near continuous stream of data on the state of their assets, whereas the budget allocation cycles to manage or repair any of the issues identified through these scanning processes, these tend to take a lot longer. It might be a 6-month, 1 year, in some cases 2-year cycles, etc. It'll be interesting to see how road agencies reorganize themselves in order to make the best possible use of this stream of data and allocate repair budgets accordingly. I don't know if you have additional follow-up insights into that particular problematic.
I think for the planning and the budget, of course, it takes more time. But if you have data from the same part of the roads over time, then you see how quickly it is degrading. And then you can also put priorities, what to tackle first, because budget will be limited. I don't know, Tim, if you have something else to add to this for this question?
The thing is that today, national road authorities, for example, or other authorities are looking at the network once a year, once every 2 years, maybe, and the data is there for 1 inspection every year maximum. And tomorrow, and in a few decades or in a few years, we will be gathering a lot of data. So instead of having 1 inspection every year, we will have a lot of data of the same place. So that will need a different approach, a big data approach, to filter out maybe some bad data and to get the bigger picture. But of course, there will be a lot of data. All these autonomous vehicles will have the eyes of these machines that will be able to make some inspections, to make some indicators, to make some assessment of the pavement. And okay, it will be a lot of data, and we need to think about how to deal with this data. But it's very rich to have a lot of data on this, but we need a smart way to go to work with this data, I think.
But that's why it should be all treated by the computers and by algorithms. Huh?
I think we'll come back to the data use issue just a little later in the Q&A segment, and how to translate that data into information and ultimately action. A couple of questions as promised on the equipment. What type of hardware is required to use the system in order to collect all the data? Can it be combined with additional data collection mechanisms, such as smartphones, perhaps in the vehicle? And ultimately, will the system be compact enough to be installed in an autonomous vehicle? I'm kind of combining different questions together here.
That's a very good question. So what you need is more on a summary on this slide. Today, it is not ready to be integrated in a car. We are working on that. We have other LiDARs. We are a LiDAR company. A few of our LiDARs will already be in the serial car, and we are modifying this one to get it also in serial car. So I'm kind of responding the last question first. And then what you need for it is actually just what's on this picture. As you have the LiDAR and a controller, and so you can manipulate online and offline and control. And that is giving them the 3 dimensions plus intensity with just this information. And if you have rich information, if you're gonna lift it up to the 6 dimensions, then you need a webcam. That's what we often use for customers. And then a GNSS, or you might have a more specialized camera together with a high quality GNSS. Those are all flexible additional sensors that you can add to the system. And if you have another sensor, we have timestamps, so those data can also be synchronized with other data collected. And that is, of course, in autonomous vehicles also required, that cameras and different sensors are synchronized and tuned together. I don't know if this answers completely, or did I forget something, Brendan?
I think it does, yes. I'll move on because we actually have quite a number of questions coming in. I'll move on in particular to potential limitations of the system. So you mentioned that the system, LiDAR does operate under rainy conditions, and we wanted to know if this was true of basically, all the way down to kind of downpour and very heavy rain. The impact of nearby traffic on readings, in particular, if there are nearby cars that might be trailing the survey vehicle, how is the signal going to, will it bounce back, and how will the reading be made? I have a couple more questions on prospective limitations, but perhaps if you would start with these two.
Yeah, sure. So rain again is a very good question. You can imagine that all the LiDARs we are working on to implement in the serial cars for different levels of autonomy, that the purpose of that is for safety, that they don't stop functioning at night, nor when it's raining or snowing or fog. And it's for that we have chosen a very specific wavelength that travels through water. I'm not talking about meters of water, but it goes through, and we even capture the reflections. And the same reasoning counts for fog, because fog is also a kind of water. So we have a LiDAR that can measure in those conditions, and that's needed for autonomous. And that's same technology we can apply for the road scanner. About the question about the near traffic, the algorithm will filter out when there are cars, as you saw during the demo, on the side. It's not going to measure the cars. But if a car is approaching the measuring car too closely, meaning that it's really driving in the field where you're measuring, then of course you won't have those measurements. And that is one of the reasons why, let me go back to the rear view for these kind of applications. You see here that we can measure very close by. And the system also allows to shut off a few bands. If we see the cars are always here, then either the algorithm filters out this data and does not account for them, or we just shut off those bands.
Okay, and can you also mitigate this issue perhaps by conducting your surveys at off-peak hours, or indeed during the night if necessary?
Yeah, then we have the full thousands of lasers. Huh? Yeah, that's and that's often chosen by customers. We already do quite a lot of road scanning this way, and that's more to have it done pretty fast. If you're stuck in rush hour, then the car is too close, and it takes you too long to do that measurement. So there are many reasons to do that.
Yeah. So more potential limitation factors. The operating speed of the vehicle, what's the kind of the acceptable range for this equipment to function, and a question more generally on LiDAR operating in a kind of mobile environment. So let me read the question in full. Typical LiDAR needs to be in a steady state so that all measurements are accurate. In this case, the vehicle is moving forward and also has some vibration in Z directions. How are these movements and vibrations accounted for in the system? And once the beams and lasers are emitted and received, there will be a possible lag, even if a short one. In this case, there should be precise GPS measurements. What is the accuracy of the GPS? And again, what are the limits in terms of the vehicle speed?
So let me go first for the vehicle speeds. I refer again to the full portfolio of LiDARs that we commercialize. The LiDARs in the car will also be applied in the German brands. And in Germany, driving at high speed. And the purpose is that the LiDAR can measure at those high speeds. So the test that we've been done for this kind of LiDAR goes up to 130 kilometers an hour, where we have still a precision about 2-3 millimeters in height. So the precision or the accuracy is not degrading linear with the speed, absolutely not. On the question of the vibrations, it's actually a lot. The full road digitization is not done by the GPS. The GPS or the CAN information of a car just give a rough estimate where this frame from this fraction of a second is positioned compared to the previous frame. And then the stitching algorithm will look for the geometry to really fit this with the previous frame. So it's the algorithm that figures out where to position, and it's not the GPS. So that accuracy from the GPS we don't need. Even if you use CAN information from the car, that's not that accurate. The IP, the high tech is a lot in the algorithm, how it figures out where to match, where to stitch one measurement to another one. And instead of that the vibration or the roll and the pitch is bothering, what our algorithm is doing, it's even calculating the roll and the pitch. So the algorithm decides how to fit this measurement to the previous measurement. Remember that the same points are measured, not all the same, but many points are measured twice, 3 times, 4 times in consecutive frames. And that data is used by the algorithm to stitch it. And then we can calculate even the roll and the pitch. If we're talking about higher frequency vibrations, this has less influence. And again, there I refer to the LiDAR developments that we are making, LiDAR for serial cars, where we have the automotive grade certification requirements. And there are, of course, the vibrations included. There are temperature constraints, there are vibrations constraints or requirements, and that we tackle anyway, whether it's for the road LiDAR or the ADAS or autonomous driving LiDAR.
Okay, perfect. I have a couple of follow-up questions on regarding the technical specifications. Let me just make sure that I run through them. Can you provide indications on the precision of LiDAR in millimeters? And would is resolution less than 1 millimeter looking at road damage? And I'm not quite sure I've properly understood that question, but if you could provide at least some indications in terms of the precision and general resolution. And can you, another question that came in, what is the max width of the scan? And do you need 1 or more runs, for instance, for a multi-lane highway? How often, how frequently or how many run-throughs would you need in order to kind of capture the full number of lanes?
So the LiDAR, that is the standard Xenotrack, goes to 4 to 5 meters. We limit it to 4 meters to have all valuable and good data. That's the width. So if we have to take the 2 ways, going and back, generally, indeed, we drive it in the 2 directions. And then we have overlap that we can again stitch. For some application, but then we need to drive at night, there's no cross traffic, we take the full width. If we put it, you can understand, if we put this LiDAR on a higher vehicle, that the width that you measure becomes wider. So we can go to 5 meters. That's really related to how high you put it. Then you can imagine that those beams are in the lateral way also wider. That comes then with a different resolution. So the standard resolution that we prefer is the 9 millimeter in driving direction, meaning you have 1 point every centimeter. If you drive much faster, then you cannot gain this resolution. You can with the software, but then you're kind of cheating yourself. And in the lateral direction, we recommend the 2 centimeter. That's also not only what the system can do better than that, but we have to limit somehow the data flow also. And don't forget that this is static. If the car is moving, those beams scan the road, and as you saw in the presentation, the little gaps that are not centimeters wide are detected. And that's partially because indeed we are scanning, or the car is moving and rolling and pitching. I hope that answers the question, Brendan. Hello, Brendan?
Sorry, my apologies, I was muted. Yes, I believe it does. Okay, a couple of questions now regarding how this data correlates with other, let's say, measurements. So is this, have you tried calibrating the IRI against, for instance, a walking profiler or other ways of kind of collecting pavement roughness indicators?
What we've done so far, and that's actually the specialist contribution of BRRC, is what Tim has presented in the extra use cases. Let me scroll through it to find them. We've compared to, now let I go back, we've compared to data, and we are still comparing to data with an APL, with a profilometer, and with a multifunctional vehicle. These are the standard known class 1 profilers with which we have been comparing. I have no knowledge of other comparison. Maybe Tim, did you do other comparisons as well?
No, we looked firstly at the raw data coming from our APL or laser profilometer, and we compared it with the raw data from the XenomatiX. So that was the first step, and then we have tried to calculate our evenness indicator, so the evenness coefficient, and we saw that we had a very good correlation between the data coming from XenomatiX and the data coming from our APL or profilometer. So this is what we have done so far. We are looking at the profile software to compare as well the IRI, but our data is coming from APL. We are also involved in this project in Brussels, where we have some data of a multifunctional vehicle. We know what is the comparison between our APL and a multifunctional vehicle. So we have an idea what will be the correlation between the XenomatiX and this multifunctional vehicle. But with the walking profiler, we didn't do it.
But as you see, what we try to do every time is go to the bottom of the raw data, which means we try to compare the road profile, not the indices. We go one step before the indices are calculated. And you can imagine if the profile looks exactly the same, then whatever indices you get out of it will be the same as well. So this is the most stringent. And as you know, an APL is not measuring the lower frequencies, which our XenomatiX can do better. We have to filter them out to be comparable with the APL data. And the same for the multifunctional data coming from a whole load of sensors.
Okay, well, let me follow up with a couple of other aspects linked to how your data correlates with other measurements. So we spoke about IRI. What about cracking, and has any work been done on automatic crack assessment and how this compares to manual crack assessment? This may be a question for BRRC in particular. And while you do think about that, another question this time linked to your measurements of marking intensity. First of all, how do you measure it? Is it measured in millicandela, for instance, and does it correlate with the type of 30-meter geometry testing which is currently conducted?
Tim, are you taking this one?
The first one with
the
cracking. Yes. Yeah. So what we are doing at this moment in Brussels is actually we have a visual inspection based on a methodology. This is labor intensive, as I said. We compare this with the multifunctional vehicle that has a system for automated crack detection, and then we compare this with the data, the 6D data, if you want. So we look at the LiDAR image, we look at the picture, and we look also at the intensity picture to try to recognize cracking and other defaults in the road. Until now, we don't have an automatic algorithm to detect this. So we are
But it's a
working on
purpose
this.
that we work on that. So we
Yeah.
see that, well, what we try to do as LiDAR specialists to get most of the data out of the 3D geometry of the point cloud, as it's called from a LiDAR, and then use the additional dimensional information to train the algorithms and to come up with the same indices. And indeed, when you talk about crack, it's not only the raw data that you can compare, then we have to go with the algorithm to come with the crack indices and compare those.
Okay, and what about pavement markings? Have you tried correlating your readings with, let's say, other specialized forms of measurements?
You mean pavement markings, so the road markings?
Yes, absolutely.
The point is whatever we measure in the intensity is in the same frame that we measure the geometry. So we know exactly where that road marking is positioned. What we do measure is kind of more a relative intensity, meaning that we cannot give an absolute value of the reflectivity of that paint to qualify whether it's still okay paint, still good markings or not. How we do that is that to use references, because we know what we measure more than just the painting, and we know what is the reflectivity of that road, and that can be different in rain and snow. Yeah, snow you don't see it, but in rain, and this way we can rescale that data to come up with qualifiers for the painting. But that is done, that is work in progress, that is not done. The road markings, absolute, so the position we have it, but to get the absolute reflectivity measurements, there we are not ready yet.
Okay, so we're now going to move over to questions linked to the storage and usage of the volumes of data generated by these scanning processes. Before we do that, Tim, one of your colleagues at BRRC, I believe, came up with an interesting additional use case that perhaps you had not thought of. We may use this technology to easily control the geometry of speed bumps, i.e. their conformity to standards, and compare with another manual method we have at BRRC. I don't know if that's a potential application of LiDAR technology that you had perhaps considered.
We thought about that, but we are working since a few months on this project, and I believe that there is still a lot of potential. There's still a lot of potential of doing other things with this data. So it's not only the speed bumps or the road markings. There is still a lot more to explore. So, but we're still in the beginning. So a lot of work in progress.
Absolutely, very much an emergent technology. All right, so as promised, questions about the data. So the data quantity is huge and complex. So first question, where is it stored? Is it, sorry, let me make sure. Oh yes, is it stored on a CPU or directly on an SSD? And is there a computer application that can analyze the data, search the data to identify specific locations that need maintenance in a priority listing? So if you can tell us a little bit about the storage of the data, the storage rate per kilometer, for instance, of survey, if you can give us a sense of that, how much, let's say, processing, post-capture processing work is needed, and ultimately, if you can briefly discuss the type of computer applications that are required then to properly analyze and make sense of all of this data. I realize it's a lot, so take questions in any particular order.
Yeah, I hope I remember them all. So at the data rates, indeed, as I said, the more precise you get, the more data you have to store. In general, just for the three-dimensional data of the roadmap, and that is processed online. So we filter out the road data, we can throw the MMA, and we keep the digital roads. You can also choose not to do that, but then you have more data. But every frame we're talking about, like, if I remember correctly, 75 kilobytes of data per frame. So if you know that we can go up to 60 hertz, and that's only the 3D geometry. If you add on that the 2D image, but the software allows to say, okay, I want just one image every 2 frames of the geometry, or 1 every 3 frames. And that are features that allow you to limit the data if you don't need that much anyway. About post-processing, so the system comes with a software with 2 licenses actually. One on the controller that is controlling the LiDAR, as I showed in the picture of where is it? This controller, where the data is stored on an external drive if you go for miles and miles and miles. Processing can be done with the software while you're doing the measurements. And so you can, for instance, simulate an APL and just keep 2 cross-sections in the longitudinal way, and only keep that data and throw away the rest. Of course, then maybe you don't need the system, but it's all possible, and that is a flexibility of the system. Most of our customers and ourselves, we keep the data, and we can drive like multiple miles and store it on the CPU. This is a controller, this is a PC with storage capacity and calculation capacity for online or offline. And with the system comes also an offline license of the software that you put on your PC, on your desk, to do further post-processing. The data that you've seen during the demo, that's just online, that's available, all the cross-sections that you can take while you're driving or afterwards. And then the further post-processing depends on what information you want. It's our finding that depending on country or state, they're different interested in different quality indices. So that calculation could also be done on the controller, but will be preferably done offline once you're back home, and then you run the algorithm on any PC.
All right, we'll conclude with a question I was planning to ask, but which was also raised by one of the audience members, and that I guess relates to the the appetite of the vehicle industry to actually share the sensor data. I think in the long-term development, you presented ultimately all the autonomous vehicles that will be rolling out of Ford and GM's factories, etc., will collect a lot of data that could be of use to road agencies. Perhaps to the type of companies that manufacture, pavement markings, for instance, providing them with feedback on how their materials are doing over time and in different weather conditions, for instance. But how willing, in your experience, are they to actually share any of that?
That's a hot topic for all the LiDAR and camera data that are integrated in those vehicles. Who is the owner of that data? And who takes responsibility? Of course, the car manufacturers like to be the owner. The LiDAR suppliers also want to be the owner. Maybe the owner of the car wants to be the owner. And then the road authorities will definitely say, well, this is my road, so this is my privacy, this is my data. So that's more a legal issue. And I don't think the decisions are taken there. Whether it's for camera data or for the LiDAR data, who owns the data, and so whether the car manufacturers are willing to share. I think if the law in certain countries says that they have to share, that they will share. And road authorities are pretty close to the legal authorities in countries, so I think that's the way it's gonna go. But I don't know.
I would like to share your optimism. I'm not sure that's the way it will go, unfortunately. But you're right. The legislation is evolving. I think a lot of people are understanding gaining a better understanding of the value of all this data that is collected, or that will be collected through these autonomous vehicles. And let's hope the regulatory and legislative framework does move in that direction. At this point, I think we will close the Q&A. So I did want to thank you, Tim and Chris in particular, for fielding all of these questions. Some very technical, others kind of a more strategic nature. So to all of you who attended today's webinar, thank you once more. So as a reminder, You will receive a PDF and a video recording of the webinar via email, and you will get this within 24 hours. In the same email, there will be a survey. We're always seeking to make our webinars more relevant to your needs, of course. So please take a minute or two to complete the survey and let us know how we've done. For now, thank you for joining us, and we do look forward to seeing you at one of our future events. Thank you, everyone, and have a great rest of the day.
Thank you, Brandon. Thank you, everybody.
Thank you.